Hello again. This is Math 1120 coming to you from the College of DuPage, and the title of this lecture is Confidence Intervals for Population Means, the rest of the story. As always, please be an active learner as you watch this video. By way of introduction, the Decisions Through Data video on confidence intervals about population means assumes that we know the standard deviation of the underlying population. This works well for the conceptual development, but in practice we seldom, if ever, know this. In practice, we actually use a different distribution for this problem called the t-distribution, and can use the sample standard deviation since we don't know the standard deviation of the underlying population. The t-distribution assumes that the underlying population is normal, and this must be validated with a histogram or box plot, but requires a different table and a slightly modified approach, but you will see a lot of similarity to the approach too. So this video provides that process. In other words, this video provides the rest of the story. Now, the point estimate, as before was, the point estimate of the population mean, mu, was a sample mean, and this is x bar. And here is a problem I would like for you to do. So here are the fuel economies of a sample, and you want to find x bar, which is going to be the point estimate, and also find the sample standard deviation for this. You know what to do. Let's see how you did. Okay, well, x bar is going to be, you add up all those numbers and divide by 16 how many there were, and you get 28.1 miles per gallon. And remember that we round statistics to one more decimal place than the raw data if necessary, and we do this only at the end of the problem. But that gives us the point estimate for mu based on this sample. And if you do this, and this is a sample, so this is going to be not sigma, but S, is approximately 2.38. Now, it's a little bit useful to talk about the history. So in the early 1900s, William Gossett worked for the Guinness Brewery, and he was in charge of conducting experiments to identify the best barley varieties. When working with beer, he was limited to very small data sets. So at the time, the model used for constructing intervals about a mean was the normal model, regardless of whether the population standard deviation was known. He did not know the population standard deviation, so he substituted the sample deviation, and he studied this. Now, while he was doing this, he found that his confidence intervals were different, and that led him to develop a model that account for the additional variability. And Guinness would not allow him to publish this, so he published it under a name, a pseudonym, and it was a student. And so this is called the student T distribution. So this was, come from Gossett, who was a chief scientist for Guinness Brewery. Here's the way the table works. Now, this is different than the normal table, so you should know that. First of all, the entries in the table, that's the things that are down here, are the critical values. And the critical values means that's telling you what are the t values. So these are the critical values that are in here. They're no longer probabilities because this is a t distribution. And what the table is telling you is, or what the table is talking about, is the area in the right tail. Now it turns out the t distribution is symmetric, and so we can have this on either side. But you see, we're talking about the area in the right tail, and the area in the right tail are these numbers across here. So those are the areas in the right tail, and these will be called T alpha over 2. And then we also have a number that's called degree of freedom, df, and the degrees of freedom for us in this problem, sometimes there'll be statistics problems where it's different, but for us it was always n minus 1. So in our problem dealing with the 16 samples for Toyota mileage, then n minus 1 would be 16 minus 1 or 15, and that would be way down here somewhere. Okay, so we've talked about that. So find the two values such that the area under the t-distribution to the right is 0.10, assuming 15 degrees of freedom. Now, if there are 15 degrees of freedom, that means there were 16 data points, and so I could be thinking about this data if I really wanted to. So the area we want to be is 0.10, and we want to find t alpha over 2. So we're trying to find this this cutoff. So let's look at our table. So we look across 15 degrees of freedom. The area in the right tail is this. So we find that the number that we have is 1.341. So you see that is the number. Now that is different, you can see, because if this had been a normal distribution, it'd be 1.28, but that's the correction that Gossett provided. And again, the t-distribution is still symmetric, but it has more spread than the z distribution. So again, you have to know to use this table and know how to use it. And here's the process for constructing and interpreting a confidence interval for the population mean. By the way, the interpretation is identical to what we had before. So the construction just is modified, but we're using the t-distribution. So to construct a confidence interval then for mu, what we do is we find x bar, and x bar is going to be in the middle. So provided sample data comes from a simple random sample, and the sample data is small relative to the population, it has to be this. And the data comes from a population that is normally distributed. And again, we've talked a little bit about that, and we can talk more in a bit. And the sample size is large. So the lower bound is going to be x bar minus, this is t alpha over 2, which we get from the t distribution, times s over the square root of n. That is the lower bound. And the upper bound is x bar plus t alpha over 2 times s over the square root of n. And t alpha over 2 is the critical value found from the t distribution with n minus 1 degrees of freedom. Now, as before, this is x bar minus a thing called the margin of error. And this is x bar plus a thing called the margin of error. Now, when Gossett developed the t-distribution, he assumed the sample data came from a population that is normal, and so some are not exactly normal, but you have to look and say, well, they're normal enough. And option 1 requires more technology than we're talking about. So option 2, you'll either look at a box plot or you'll look at a stem plot to see if it's close to that, and you'll see us do this in one of the examples. But there is a normality condition, but it doesn't have to be exactly normal. So let's then do a problem, and we're going to construct a confidence interval about a population mean, and we're doing it for this same set of data. These are the mileage for a set of 16 Toyota Camrys, and so this is the data we've been using. Okay, so first of all, we're going to take this and we're going to verify that it does satisfy all these things, and that it's more or less normally distributed. We're going to use a box plot. Then we're going to compute x bar and s. Actually, we've already done that. We're going to determine the critical value, and we're trying to find a, let's see, 95% confidence interval. Okay, so this is a 95% confidence interval. That means we have 0.25 is the area to the right of the critical value. Okay, so this is what we have. We've already found these, so let's look at the work. Here's the box plot, and you say it's not exactly normal, but it's good enough. So we did the box plot here. For step 2, we find out that the standard deviation is 2.38. We did that earlier, and the mean was 28.1. Now, for a 95%, what we're going to do is we're looking for, and n was 16, so we're looking at 15 degrees of freedom. And so if we look in the table, we will see that this is 2.131. You should confirm that you have that. So then the lower bound on the confidence interval is going to be this. We plug in the numbers. And the upper bound on the confidence interval is going to be this. So the statement then is we're 95% confident that the mean miles per gallon is between this number and this number. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.